So thanks for the introduction. So this is joint work with Markus Müller-Olm, Christoph Ohrem, and Jens Gutsfeld. So to start, we consider the following example scenario, which I will use as a running example throughout this talk. So suppose we have a server that consists of a main thread, and this main thread can receive different kind of requests from different clients, and it processes each of these requests by starting a worker thread that then processes these requests and then gives a certain response to that request. Okay, and in this scenario, we now want the system to satisfy the following properties, which I refer to as properties P1 to P3 here. So first, the main thread should repeatedly accept new requests. And then second, we want that worker threads are only spawned by the main thread and not, for example, by other worker threads. And they should only be spawned if the main thread has accepted a request and not at any other time points. And third, we want that worker threads are also only spawned if we are inside a certain procedure called PR. For example, because this procedure performs some bookkeeping about all threads that are currently active. Okay, and we now want to verify that our system indeed satisfies these three requirements. And so these properties are essentially temporal properties of executions of the system. So this looks like a good way to use verification by model checking in order to achieve this. And in order to do this, we have two things to do. Namely, first, we need a formal model in which we can represent this example scenario here. And in particular, this model needs to support some notion of dynamic thread creation, because here we have a main thread that should dynamically spawn worker threads during the execution. And it also needs to support some notion of procedures so that we can even reason about the third requirement, P3 here. Okay, and second, when we have a formal model, then we will also need a specification logic that we can use for indeed specifying our three properties here. So for the formal model, we use an established model called dynamic pushdown networks, or DPNs in short. And this model essentially takes pushdown systems and extends them with dynamic thread creation. So during execution, we can now have multiple threads. Each of these threads can behave as in a pushdown system. So during the execution, each thread is in its own local control location, and it can operate on its own stack. And all threads can progress like that independently of what the other threads do. But then additionally, each thread also always has the option to just spawn new threads at runtime. So this is a quite useful type of system for modeling concurrent programs, because we have stacks for modeling recursive calls, and we can model multi-threading. We can just dynamically spawn new threads. Now we model executions of this model as graphs, and here you see an example. So each node in this graph corresponds to the local configuration of a single thread of the execution. So for instance, in the first row here, we have the nodes for the initial thread, and then the edges between these nodes just specify which type of action the thread performs when moving from one configuration to the next one. So we have a call edge if the thread pushes some symbol to its stack. We have a return edge if it pops some symbol from its stack. And we have an internal edge if it performs just an internal step. And moreover, as in nested words, we also use nesting edges, which are depicted as these curved dashed edges here, to connect call actions with their matching return edges if they exist. And finally, when the thread spawns a new thread, then we also just add a spawn edge here, which connects the position where the thread is spawned to the first node of the new thread that is spawned here. And you also see that all nodes are labeled here with some set of values. So these values are just atomic propositions here that we will use for specifying basic properties in our logic. So we just say that each node is labeled by all propositions that hold in the corresponding local configuration that is represented by this node. So maybe you are wondering why we are using graphs for modeling executions of our system, because typically the semantics of DPNs or similar models is defined as an interleaving semantics. And then we would define something like a global configuration that consists of multiple local configurations that each represent the state of one of the current threads. And then a step in this semantics consists of a step of one of these underlying threads, so that we can then reflect different interleavings of the threads in different executions, because executions are then just sequences of such steps, and thus, well, two different interleavings just mean that we have two different sequences of such steps. But one big problem with this kind of semantics is that it often allows the encoding of the intersection problem for context-free languages quite easily. And if this is possible, then this would make all our verification problems immediately become undecidable. And so in contrast, in our execution graphs, we do not have this notion of different interleavings. So if you go back to our example, here for these two threads, for example, this graph does not specify how the actions of the two threads are interleaved after the second thread is spawned here. So there would be multiple executions in interleaving semantics that all correspond to this single execution graph. And so this also means that we will not be able to reason directly about a specific interleaving in our specification logic, because this information is just not visible in our semantics here. But our execution graphs still contain some other useful information that we will be able to talk about. So first of all, it contains information about the temporal behavior of single threads of the execution. And this includes, in particular, information about the call and return behavior, which is given by the nesting edges here. And it also contains some information about the thread spawning behavior, which is given by the connection of the different threads via the spawn edges here. Okay, so what we want to consider now is model checking for DPNs. And the only approach for this so far is called single index LTL. And in this approach, we can essentially check single threads of the executions against LTL formulae. And well, this is sufficient for expressing some interesting properties, like our example property P1 here. But for expressing our properties P2 and P3 here, we need a more expressive logic, because P2 talks about when threads are spawned. So here we need to reason about some kind of the thread spawning behavior. And P3 talks about being inside some procedure. So in order to express this, we also need to reason about the call and return behavior. And our contribution thus is to develop a suitable logic here that we can use for specifying all these kinds of properties. And of course, we not only define such a logic, but then also investigate the corresponding model checking problem. So our novel logic is called navigation temporal logic, or NTL in short, and its syntax is defined here. So an NTL formula is always evaluated in a given node of an execution graph. And then first we have atomic propositions to state that, well, some proposition holds in the given node of the graph. Then we have the standard Boolean operators just as usual. And then most importantly, we have these formulae of this form next f phi. So these formulae can be used for navigating through the graph by saying that from the given node, there exists a certain successor node in the graph, and then this successor node satisfies the formula phi. And the parameter f here is, specifies which type of successor is used here. So we have 6 different successor types in total that we can use for following the different kind of edges that we have in our graphs in different manners, either in a forward or in a backward way. And 4 of these successors come from a logic for pushdown systems named carré. And so these successors can be used to navigate to different positions inside of a single thread. And we then also add 2 new successors here so that we can also follow the spawn edges in the graph, either in a forward or in a backward way. Okay, and then we also have a least fixed point operator. And with this operator, you can express all the classical modalities that you may know from LTL or carré, like until, finally, globally, and so on. And so this is an example of a formula that expresses that the formula phi holds finally on the path that follows f successors. So as you see here, these modalities also come with this parameter f here that specifies which path is considered here by saying which type of successor we want to move on from the given node. But we can now also combine multiple of our successor types inside a single fixed point formula for expressing even more properties that we, for example, could not express if we just had an until operator for each single successor types, as we do have, for example, in LTL or Carré. And this is an example of such a formula. It specifies a very reasonable requirement here, namely that the property phi should hold just in an arbitrary node in the graph. And here we need two different successor types to express this, because in order to reach all nodes of the graph from the initial node, we need to move forward both inside of the current thread, but we also need to move to new threads when they are spawned. So that's why we have two different successor types here. Okay, so now let's go back to our example properties and look how we can express them in this new logic. So first of all, you see that all our formula here start with this special globally modality at the beginning. So this is just a dual operator to the last example from the previous slide, which just means here that for every node in the graph, something holds. And then the first property, P1, can be expressed by a simple LTL formula inside this globally modality that just says, well, if we are in the main thread, then we always eventually accept a new request. And so this is an LTL formula here, but thus it's also an NTL formula. And for the second property, we can express similarly that if we are in the worker thread, then some other condition holds. And so what we want to say now is that at the position where this worker thread was spawned, something holds, namely that at this position, we are in the main thread and we have accepted a request. And well, fortunately, we have a next operator to express exactly that. So the successor type that is used here is one of our new successor types that just moves from a given node to the position where the current thread was spawned. Okay, and finally, our third property can be expressed by this formula at the bottom. So the successor type, so this next formula that is used here just follows a spawn edge if it exists at the current node. So that this here just means if we spawn a worker thread at the current node, then this formula at the right holds. And then the successor type that is used in the finally operator is called the caller modality, and it just moves backwards to the latest previous call position that has not been matched so far in the thread. And well, using this in the finally operator like this here, then just means that at some previous call position that is unmatched so far, procedure PR is called. And well, this then just means that we are inside this procedure because the procedure has been called before and the corresponding call has not been matched so far. Okay, so now that we've seen some examples, let's take a brief look at the corresponding model checking problem. So in this case, this means we have given a dynamic pushdown network M and some NTL formula phi, and we want to verify whether all executions of M satisfy this formula phi. And we use an automaton-based approach to solve this problem. So at the end, we will reduce the whole problem to the emptiness check of a certain automaton. And one type of automaton that we use for this are called two-way alternating parity tree automata. And so we want to use these automata because their features very nicely match with the definition of our NTL formula, which makes the encoding of these formula into these kind of automaton very easy. And so, but one minor problem here is that these automata work on trees, as the name suggests, while our executions are actually defined as graphs and not as trees. But this is in fact not a huge problem because we can just do a simple transformation to transform these graphs into trees. And so what we essentially do is we just discard all the return edges in this graph. So this is indeed a tree now. And this is a useful transformation because first, we did not lose any information here, so we could retrieve all the missing return edges just by inspecting all our remaining edges here. And the set of all trees that are obtained from execution graphs by this kind of transformation is a regular set. So this also means that we can use a tree automaton to recognize all our valid input trees that we even need to consider. And this transformation now allows us to use these two-way automaton to check whether an NTL formula is satisfied at a given node. And this feature, so two-way means here that we can navigate freely in the tree, both upwards or downwards whenever we want. And this makes it easy to check our different next formulae, because in order to check that the formula next f phi is satisfied at some given node, where we can just move to the desired successor node wherever it is in the tree, and then check whether formula phi is satisfied at that node. Okay. And we can then indeed reduce this whole model checking problem to the emptiness test of an automaton. And finally, we obtain that the whole model checking problem for our novel logic is x time complete. And more precisely, it is exponential only in the size of the formula, but in particular, it's polynomial in the size of the model. And well, usually in model checking, it's the model that might become very big and not the formula. So this is actually quite good here. And this is, in fact, the same complexity that we already have for LTL model checking against pushdown systems. But, well, now we considered dynamic pushdown networks here, which are strictly more powerful than pushdown systems because they also support dynamic thread creation. And we developed our new logic, NTL here, which is strictly more expressive than LTL for single threads, because it also allows reasoning about the thread spawning and the call and return behavior. It's both not possible in LTL for single threads. And besides model checking, we also considered the satisfiability problem for our new logic, and we show that this is also x time complete. Okay, and finally, for future work, we also want to consider some more powerful variants of DPNs that also allow synchronization of different threads via locks or communication between different threads via communication channels. Okay, so that's all. Thank you for your attention.
We have time for some questions.
So the threads, they are completely independent in their execution. It's like disjoint parallelism, right? And
Yes.
this allows you to, because now every linearization of the tree, every total order of the spatial order is a possible execution. But this is no longer the case when you add locks or when you add communication. So then the trees will no, I mean, these graphs will no longer be useful, right? I mean, can you still use the graphs when you add locks or when you add communication? Because then not all interleavings are possible.
So that's true. So we need to consider the fact that so I think we can still use the graphs, but you're right, we have to keep in mind that we have to check that whether this is even executable at all and how executions are possible then. So some more work to do then.
Did you look at the possible connection with what people call spatial logics? So logics, modal logics that talks about distribution and trees and processes moving. For example, the ambient logic of Cardelli and Gordon, and there are many other instances.
Sorry, I'm not understanding.
So spatial logic, it's a category of modal logic that talk about space. And so you can also add temporal modalities. Did you look into that? Or?
So I'm sorry, I cannot say anything about this work yet.
Okay.
It's too old.
So maybe just one question that's related to Andreas's. So, and then we move to the final talk. So, do you think if you only retrieve the Boolean result of a thread, that you will still be able to use trees to represent things without loss of information?
So, and no locking or other
So I just want to know, okay, did this spawn thread result in a true or in false when it was finite?
Yes, so this should be possible, yes.
Okay, thank you. Any other questions? Okay, so can you just...
So your examples, they did not talk about the call return discipline, but I guess that you can still express things like some function is not called before some other function has returned,
Yes.
like in caret.
Yeah, yes. Everything that you can express in caret, you can express in this logic.
Okay, good. So then if there are no further questions, let's thank the speaker again.